We're back. We're back with the second part of the second day of Journées Scientifiques Inria, Chile. Next, we're having another activity that will show us the clear DNA of Inria, Chile and the French-Chilean bond, not only through the promotion of research excellence, but also with the strong connection to innovation, which is a clear part of the mission of Inria, Chile. To continue, we will learn about successful cases of collaboration with industry as a result of this strong connection between high-level applied research with high impact in sectors like health, precision agriculture, and also astronomy. Remember that during the presentations, we will be receiving questions through the question chat. Please use the question chat. The chair of this session will be Stefan Dalmas, who is an innovation advisor at the innovation direction at Inria. Stefan is PhD in computer science and spent 12 years researching various topics in computer algebra at Inria. In 2000, he joined the Technology Transfer Office in charge of industrial relations at Sofia Antipolis. Since then, he held various positions at the Central Technological Transfer Office of Inria as Executive Director of the Inria Carnot Institute and Head of Industrial Relations under the Deputy CEO for Transfer and Industrial Partnership. Thank you, Stefan, for joining us and sharing this important session today. Okay, well, Stefan is having some troubles with some issues with the connection. We are waiting for him to connect. However, we are working right now. Yes, we are working right now to solve this problem. So he will be back with us. Meanwhile, I will continue with the presentation. The first case is smart agriculture, frost forecast. Yes. Frost prediction in smart agriculture presented by Thomas Watain, Research Director, AIO Team Lead. Frost events during the vineyard blooming period in the spring can ruin a year production in just a couple of hours. The Frost Forecast project uses a network of low-power wireless sensors deployed throughout the vineyard, coupled with advanced data analysis tools to predict frost events. They use low-power wireless technology standardized by Inria AOIO in Paris. The Inria Chile team has deployed the resulting solution in the Concha de Toro vineyards here in Chile. Frost forecast is a perfect example of the symbiotic relationship between the scientific excellence of Inria and also the Chilean ecosystem, with Inria Chile serving as the catalyst.
Hello and welcome to my lab here at Inria Paris. My name is Thomas Watain. I'm a research director and lead of the newly created IO team. And it is an absolute pleasure to be talking to you about frost forecast, frost prediction in smart agriculture. So what are we talking about exactly? We're talking here about a problem that exists on any sort of fruit trees or fruit things that grow, and the problem is late spring frost events. If early in the year, during the spring, it gets too cold, the flowers or the different buds can freeze, and if they freeze, they fall, and if they fall, there's no fruit that has been created, and that's a large problem. It is something that is very costly. You can see here the numbers for Chile, for Europe in 2017, for France itself in 2021. And you can see that there's a massive, massive project for any producer, including vineyards, of course. There are ways for producers to combat this. If they know that there's a frost event coming, they put in place mitigation strategies. You can see here using fuel heating, or throughout the vineyard that is lit up so that they heat up just by a couple of degrees. There are some solutions based on sprinklers or irrigation, some solutions based on wind machines, but all of these are costly and some of them need some time to install. And so what is hard is not really to combat the frost event. What is hard is to know when it happens so that the mitigation strategies are put in place at the right time. And this is exactly where the frost forecast application happens. It is a fantastic collaboration between a couple of entities. There is my team at Inria here in Paris, providing the low power wireless mesh network and low power wireless sensor networking technology. There's of course Inria Chile, who serves in the middle point here and putting all of this together and adding, of course, an enormous expertise in terms of machine learning and cloud infrastructure. And then there's the end user, which in this case for the deployment I'm going to talk about is Concha y Toro, which is one of the largest wine producers in Chile. So what we have developed, and the frost forecast solution is a network of low power wireless devices that are deployed directly in the vineyard. What you see here in this slide are the different nodes, the different frost forecast nodes that are these poles, and then they are connected together wirelessly through a low power wireless mesh network and reporting their information in real time through a gateway to the internet and collecting sensitive information in terms of temperature and humidity at different levels throughout the vineyard. So what type of networking technology are we using? This is my contribution to the project, or the contribution of my team to the project, is on the networking side. And so in my team, we are developing a solution based on time synchronized channel hopping, or TSCH, a networking solution that we are developing within the team, deploying within the team, and standardizing within the team. In a TSCH network, the key to it working is that all the nodes are synchronized, and when the nodes are synchronized, we cut time into time slots, and then we have a communication schedule that fully orchestrates the communication within the nodes. And what you see here on the right-hand side is a representation of a low-power wireless mesh network that you see here, where the gateway sits on top here, and then here you have a number of nodes. In the previous picture, those number of nodes would be those poles. And then here is the scheduling of the communication, telling each node what to do at what point. The goal of this, and why this is the technique that we're using, is that time synchronized channel hopping achieves extreme low power consumption. Each of these nodes is asleep way more than 99.9% of the time. Years and a decade of battery lifetime for these nodes. And then because, as you might have guessed here on the y-axis, because we're using several frequencies, by doing this channel hopping, the nodes are able to cope with external interference or multipath fading, resulting in extremely reliable communication. And so the combination of time synchronization and channel hopping gives us wire-like reliability and years of battery lifetime. This is a technique that we have been developing within my team, and is a technique that we are standardizing as well. So we created a working group at the IETF, the Internet Engineering Task Force, which is the standardization body between a lot of the internet today, where we are standardizing the stack that I show here on the right-hand side. And you can see here under this name 6-ish for IPv6 over the TSCH mode of IEEE 802.15.4e. So this is a technique that we developed within the lab, and we have been deploying this over the last couple of years. Here you see some pictures of previous deployments where we have been using these systems in environmental monitoring in California, again in California in wildfire preventions, in Argentina, monitoring in smart agriculture projects in different orchards, here in France, in smart parking for boats through a startup company that we created in 2019. And so we have a lot of experience deploying these systems. And so when Inria Chile approached us for the frost forecast project, we were extremely excited in using this technique in the vineyards in Chile for frost prediction. What I'm going to show now is a little video of the first thing that we did within the team here in Paris, was to prepare the low power wireless solution. You're going to see us building different little boards. You're going to see us assemble different elements, and then you'll see how these are deployed in the vineyards. This is my lab, and you'll see that we have the full resources to make these little devices. So here you see Trifun Savic from my team assembling one of these boards. These are boards that were designed here in Paris, and you see him applying some solder paste through a stencil on a board, and then picking a wireless communication module and putting it down at the exact right location on that printed circuit board. And here is that board is going to a reflow oven, which causes that solder paste to melt and to attach the different electronic components to the PCB, to the printed circuit board. Once that printed circuit board is ready, he's assembling the last components. Here you can see the antenna. And then Jonathan Munoz is taking over and doing all the programming. So here you see Jonathan writing the firmware on these devices, meaning, of course, all the networking aspects that we've talked about just now, but also the application that is going to read the different sensors and then report them wirelessly. These boards that you see here on the desk have some plugs. You can see here on the right-hand side 4 little plugs that look like Ethernet plugs. This is where the sensors connect to. And so, as you will see in a second, we deploy these nodes in a vineyard connected to a number of temperature and relative humidity sensors at different locations on a pole within the vineyards. Here is the map of the deployment area. This is in El Triángulo at Concha y Toro. And the nodes that you have here, these little icons here represent the nodes that are forming this low power wireless mesh network and sending their information to a gateway, which is positioned here centrally, collecting all the data. So that gateway looks like this. It is a box that is closed that can resist rain in particular, and that consists of a Raspberry Pi single board computer connected to the manager, to the gateway aspect of our low power wireless network, and then through a dongle connects to the cellular network. And here you see the Inria Chile team assembling the different poles that will be deployed in my lab. So these are the enclosures that protect the sensors. Along the pole runs those cables that bring the signals down to this board that is at the bottom here. You will recognize the board that we have fabricated in Paris. And here the team is loading up the poles that are going into the vineyard. And you will see the team now installing those poles. So going in strategic locations, protecting the bottom side of the pole, and then digging a hole and installing the poles. These poles, so of course, these devices are entirely battery powered. There's a battery inside the little box at the bottom there, and then that is powering the whole thing. There's absolutely no need to bring any sort of power to these devices as they are deployed. This information is then gathered, so in real time, a couple of seconds after it has been measured in the field, the team at Inria Chile receives the information, and what you see here is the live view of the data coming from the field. And of course, this is just raw data. The actual platform, of course, does the data analysis and the frost prediction. So here you see the platform. The data sources here, what we represent here are the data sources, including low power wireless sensors that we have deployed in the field. This goes through acquisition, becomes raw data, and then through a number of processing steps, this is then being transformed into predictions of frost. The team, so again, my team provides the low power wireless networking capabilities, and then the teams of data scientists at Inria Chile develop the graph neural networks around this to be able to turn those raw data measurements into frost predictions. So where are we in the project? This is a 3-year project. We're beginning the last year. The network was deployed, the network was developed, as you can see, and deployed and installed. And we are now in 2022 working on the predictive models, a version 2 of the predictive models, and a version 2 of the user interface. I would like to come back to one of the slides that I already presented and to this slide here, and I want to highlight the exceptional role of Inria Chile in this adventure. Inria Chile plays two roles. First, as an orchestrator, Inria Chile is capable of taking technologies from different teams within the pretty large Inria ecosystem and identify the right technologies, identify the right team, the right end users or use cases that presents themselves. And so as an orchestrator in this particular project, they're bringing together their expertise in data analysis and machine learning, the expertise from my team in low power wireless networking, together with different use cases. And I presented only one here, which is the vineyards at Conchaitoro, but there are other applications in smart agriculture on different types of crops that are being explored. So as a orchestrator, Inria Chile is able to put all of this together and own really the system and the deployments as you've seen in these slides. And then they also serve the role, a real role as a catalyst, putting together these different teams and adding their capabilities, and as a catalyst, making the full system work all the way from the sensors, in our case, all the way from the sensors to the cloud to the end user. Thank you so much.
No, we have some problems in hearing you right in the right way. So what do you think about the ideas so that I can present the case, the astronomy case, and maybe we can see with the technical support team maybe what we can do about the connection. But let's move on along with Stefan. So the next case is the case of astronomy with the project Love LSST operator and visualization environment, presented by Andy Clements, his telescope and site software manager LSST at the Beta Rubin Observatory. He will provide an overview of the work being done at the Beta C Rubin Observatory by Inria Chile. We'll leave you now with the next topic.
Hello, my name is Andy Clements. I am the software manager for the Telescope and Site Division of the Vera C Rubin Observatory. And I'm here to discuss what work Inria Chile is doing for our telescope. First, an overview of Rubin Observatory. It's located on Sierra Pachon in Chile, near La Serena, about an hour east of there. The whole goal of the telescope is to complete the 10-year legacy survey of space and time. The telescope used to be named the Large Synoptic Systems Telescope, but we've changed it over to Vera C Rubin, and in order to keep the LSST moniker, we have this survey. We've named it that. The four main science areas that the survey hopes to accomplish is probing the dark energy and dark matter areas, taking an inventory of our solar system, checking out the transient optical sky, and essentially taking a map of the entire Milky Way. It hopes to do this by completing an entire survey of the southern sky in 3 nights, which is something that has not been done before. We need a lot of fast working technology to do this. This includes our 8.4 meter boron silicon mirror, which combines our M1 and M3 mirrors together into one substrate. This also includes our 3 billion pixel camera, which is put in the Guinness Book of World Records. These two items will help put together 20 terabytes of data every night and send them off to various places such as the States, Chile, France, and England. The telescope itself is still under construction, but we hope to have it completed about late 2023 or early 2024. The four main divisions for the construction phase of this telescope are the telescope in sight, which is essentially the observatory, the telescope, and all the auxiliary areas and devices that are associated with it. There's a data management division that takes care of all the data coming from the camera and going to the states and whatnot. There's the camera division, which kind of is self-explanatory. And then EPO, which is the Education and Public Outreach. And they work with all the kids and the public and the scientists to get this information out there and start the science with everybody. We have our website here down here. It's, as you can see, still lsst.org. It's a lot easier than trying to move everything over to veracrubin.org. So why did we choose Inria, Chile for this? Well, we needed to generate control room software, and we needed UI expertise for this. The main reason is, from an HCI point of view, the Rubin Observatory Control Room is a kind of a mission critical system, especially in terms of safety, because we're going to have this humongous telescope rotating around and a dome that's rotating around. And we need to make sure that folks and machines are safe and well taken care of, and that the information that is coming from those machines and those computers comes to the observer and is displayed in such a way that accidents or damage cannot occur. This is also kind of a one-off telescope. This has never been built before. So there's a lot of customized nature of the system itself and how we're doing things, especially in the fact that we're trying to survey the entire sky in 3 nights. So they showed to have the expertise in these areas. And we've kind of did some back and forth with them to see what they could possibly do with us, and that definitely kind of fitted our bill. They've also done previous work within telescopes. They've done work with ALMA doing their alert systems over there, and some with the Chernobyl telescope array and a few others. We worked with some of the HCI experts that are with Inria, including Dr. Gutierrez, who was with us for a good part of the beginning of this. So the scope of the project that we have with Inria, Chile, is first off, as I said, the generation of the control room software. And we ended up calling this the LSST Operator's Visualization Environment, which is short for LOVE. That includes a lot of the major telescope components that would go on, which includes, as you can see here, the dome, which is a 3-ton dome that rotates around, the TMA, which is the telescope mount assembly, the M1, M3 mirror, which I talked about, but we also have another mirror, it's M2. Both of those have cells that the mirror sits on that need to be controlled, heated and cooled, and or moved in order to get the best optics from them. There's a hexapod rotator on the camera as well as the M2 that need to be controlled. There's the active optic system that take the light going through the telescope and needs to be able to adjust it for the best optics possible. There's our pointing, so we know where we're going through, the calibration of the telescope itself, so we know how well it's working. There's an auxiliary telescope over right next to the main telescope that actually measures the sky and the pollutants and everything else to give us an idea what kind of atmosphere we're working with the images we're going to get. And there's the entire telescope control system, or the TCS, that takes in essentially all the telescope controls itself and allows the telescope to move according to directions of like the scheduler and stuff like that. There's also not only the telescope components that this has to handle, but the major observatory components as well too. We have a logging system that not only taking the logs from all the computers that are there, but the observers and the engineers and everything else that works with the telescope, so they can work in concert to figure out what problems are and fix them before they get too serious. There's the EAS, which is the Environmental Awareness System, which includes a whole slew of components like the weather station, the DIM, all sky cameras, the environmental enclosure control, the HVAC system for the air conditioning, the whole thing, and then monitoring everything else, as well as facilities. And it's we also have a main component for that called the Observatory Control System, which is the OCS, which controls a lot of this. Inria, Chile also has to help us monitor our server and network stuff that IT is working with, and also the GIS, which is our global interlock system, which is done by our electrical stuff. All this stuff goes onto our middleware, which is a data distributed system. We're using AdLink, Open Splice over there. We built an abstract layer on top of it, which is the system abstract layer, SAL. We call a lot of things SAL components, essentially. They're working with SAL. All the telemetry events and controls commands go on the SAL. The love system that Inria Chile built takes all those commands, events, and controls and displays them accordingly. The data that's there in a nice recognizable format that the operators can do. And a lot of this data also then goes into an engineering facility database, which is essentially Influx. The Inria team is also pulling data from there for past information and stuff like that for comparison as well too. They also helped us set up the control room as well too. As you can see in the picture over here to the right, there's still a lot more to put together there. We're just getting started with it. But it's already in use with the auxiliary telescope. We've been doing observing runs with that, and it's been working really well. And also that beyond the scope of what we already have, we've been adding more on there. They've been doing such a good job. We've been giving them more work. This includes some of our authorization components. We've put in a control room display for that, as well as some more logging that comes with it. The project timeline has been a little different than most things we've ever done. When we first started this out, the Rubin Observatory really had no idea what they wanted. It was hard to kind of generate requirements without some ideas and stuff. So we divided everything out into two phases. The first phase was essentially them just putting up a prototypes to see what things would look like. And so we get feedback from the scientists and operators to figure out how we were doing this. This was a little under a year that we put it together. We were able to put these prototypes together and pass them around to everybody, get a lot of feedback, generate an entire list of requirements that are needed for this, and putting together in a document, along with a statement of work as well too for the next phase, which is essentially assembling the entire control room and its displays. We divided this up into two, mainly for accounting reasons. The first part was to put together like a user interface framework, as well as displays for the auxiliary telescope. This is kind of like a preliminary test for everything. We generated it all together 2 years ago now, and put it up for a final design review. That design review passed with flying colors, I must say. Everyone was pretty happy with it. That allowed us to go on to part B of phase 2, which is now putting in the main telescope, which is still being built there, and the environmental awareness system, which I talked about, as well as observatory control. Inria Chile's been really good about working with us as we're slowly building these things together. Sometimes some things get delayed and some things get pushed forward, and they've been able to work with us to go back and forth with this to continue to make progress as well as get things accomplished together. And that pretty much is the whole overview of what I've got with the work that goes with the Vera C. Rubin Observatory and Inria Chile. Thank you.
Stefan, can you hear me?
Yes. Can you hear me?
Yeah, now we can hear you loud and clear. So please, what do you think? Will we move on with the next case? Can you maybe talk a little bit about that?
Yes. So our last talk will be about a project funded by ANID, which is the the Chilean research agency. And it's a project about artificial intelligence and medical imaging. And the Inria participated in the in a content-based image retrieval system. So let's watch the video.
Hello, my name is Mauricio Araya. I am professor for the telematics engineering at the electronics department of the Santa Maria University. Okay. For those that do not know my university, there's a nice picture of our Valparaiso campus near the sea, but also we have campuses in Santiago and Concepción and Viña del Mar. I will talk today about the successful collaboration that we had with Inria, and we are continue having with Inria around the ALPACS project, which is a project funded by ANIT, the National Research Agency, and specifically about proximity, which is an application that it's connected to ALPACS. So the problem that we're trying to tackle is to making artificial intelligence available for a diagnosis in medical images, okay? And there is a huge gap between very advanced digital imaging systems, like the different instruments that you can find in a hospital, with applications that we usually use nowadays that use AI in your cell phone or in your computer. And this gap has several different reasons to happen, and we are trying to fill them, okay, in order to reaching artificial intelligence for people, for patients. And the obvious one is that current artificial intelligence work with data, and you need specific learning models for that works with that data. And I will argue that this is the easiest part of the gap to fill, because you can go to the state of the art. That's the good thing that we do in academia. We share information, and you can find the best models that the state of the art give you for doing that. But unfortunately, for training this model, you will need information, you need data. And these different systems works like islands of information, because each hospital, each clinic will have a very different system, and they do not talk with each other. And this is not because they do not want to do it, it's because they are constrained by the data privacy and ownership of the data. Because an image of you, it's owned by you, and the different hospitals, the different clinics just have to protect your data privacy. So that's another problem that we have for having artificial intelligence, because you cannot have a lot of information to train. The third one on the other side is that it's not enough to having a very advanced model or a very advanced algorithms that solve the problem, but also this need to be used by practitioners. So you need to have these applications work not only good, but integrated with the whole environment that the practitioners use in the hospital, in the clinic. So that's another gap that needs to be filled. So what we have done in ALPACS, it's basically that, okay? Trying to make the health data available for data mining, for making predictions for diagnosis. And for that, we try to fix this problem of information islands through interoperability, having a repository that can be copied in different institutions, and the data privacy and ownership solved by anonymization, okay? So the constraints that are by law are now included in these ALPACS in order to protect the data without making the data unavailable, okay, which is a huge problem. And on the other side, we need to test that this could be used for artificial intelligence, and that's where the proximity application or prototype has been developed. So we use deep learning models to produce usable content-based search of medical images. And that's the successful story that I want to talk today with Inria, okay? So ALPACS, it's basically an architecture. I will not go into the details on this. It's an architecture that anyone can copy, and they will have an anonymization system that allows to interact with other data and allows to talk with different centers, okay? And that will produce enough data to having applications like proximity, okay? So what is proximity? this is a tree-like navigation system for finding similar images based on content. So when you search in Google, you will search for a tag, a text that someone has put over here. So the difference about this is that now you upload an image and you try to find images in the context of medical images that are similar to them. And for that, you can upload your image or get it from the packs, and then you can use content-based image retrieval system here, based on deep learning and graph theory, in order to produce this type of graphs that allows you to analyze what are the different diagnoses and what are the different similarities between one case and the other. And that's what we have developed side by side with Inria. So we have the idea, we have the expertise for making these models, but have no much clue on how to construct the application. And that's where the collaboration with Inria start to happen, okay? The Alpax project had Inria as a partner, so we started to discuss how to construct this tree-like graph, and we have a very fruitful collaboration that it's completely recorded in Zoom meetings, because this was in the middle of the pandemic, and you can see that the intellectual property is of the both, because we have worked with into developing the whole interaction diagram, the different algorithms in order to produce this very specific type of graphs, and the application itself as a joint project. And actually, Inria has developed a lot of the basic part of the front end of the application that we have now, okay, the prototype. And this was several meetings where we put some objectives and work in collaboration with the group of Andres Viñata and oversight by Luis Martin, okay? On the other side, we have also collaborated with Inria on getting this idea right through workshops and asking to the community what they thought about our work. So the first workshop was actually organized by Inria mainly, and we help a little bit. They bring the keynote speaker and start the presentation, as we can see here, in order to invite a different types of projects that were working on artificial intelligence for medical images. And it was a very good insight as to produce this new workshop later, specifically on content-based search in medical. Part of this workshop, and was a very productive one. Moreover, these funded projects, this type of projects that are funded by the National Research Agency, need to have a board of directors, which are all the associated institutions that work in the project. And actually, the director of Inria, Nayat, was the president of the board, and the board helped us a lot to solve some huge problems that we had with the project in some points. As you can imagine, this type of research or applied research need to work side by side with hospitals. And when it arrives the time to work with them, we were in the middle of the COVID crisis. We were in the middle of the saturation of the hospitals. So we didn't feel that was the very good time to ask them to develop these nice applications. So we had a problem that started to the project to be late and to have a few problems with that. And actually, the board of directors helped us a lot to refocus the project, to work in COVID data. The COVID data was available and helped us to solve that problem, and has a very good evaluation of this project. So it was very important, the collaboration of Inria on this also. And this project do not stop here. We have a very good evaluation, we have a prototype, but actually we need to continue working. It's not enough to have a nice prototype that could be published, and it was published, but we need to go to the pilot stage where we can go and do this in the medical department that do the diagnosis. So we have applied for a second FONDEF project, and this was approved. So we have this repositorio interoperable para análisis inteligente de imágenes médicas as the second part of the project. And now we have integrated Universidad de Chile as a full partner of this project, besides Santa Maria University, and also with Inria Chile and other companies of the private sector, in order to having now a larger pilot stage and not only a prototype. And this pilot stage has been approved by the ethical committee of Hospital Clínico Universidad de Chile to make a differential diagnosis study over 10 years of images on the Hospital Clínico Universidad de Chile, okay? Specifically, thorax computational tomographies, okay? And we have more than 10 years of those kind of diagnoses in order to make a study on differential diagnosis. So this project continues. We are very happy with our collaboration with Inria in the sense that there was not only giving ideas but actually working side by side, making code and talking with us with a different perspective that help us a lot to have a more inclusive project with different ideas and not only from the academia. So just a thought, that to close up, successful collaboration in order to having applied research, to have innovation and transfer, needs to have for sure a good number of capabilities. We were working before this on artificial intelligence for astronomical images, but you need the people that are well involved in the domain in order to make a successful collaboration. So you need the university, you need research institutes like Inria, you need the hospitals, you need the public sector, you need the private sector. And collaborations are not easy, but it's the way of getting research from the sky of research publications to reaching people and patients. So that was my presentation. I hope you enjoyed this kind of innovation and transfer initiatives, and we will be very happy to report you in a few years how this has grown and how our collaboration it's better and better each year. So thank you very much.
So thank you to Thomas, Andy, and Mauricio. Now it's time for questions. So I have a couple first for Thomas. The first one is, could you give us an idea of the size of the project as an estimated cost, or maybe the number of person-months spent on it?
So yes, I'm trying to turn on my webcam. Can you hear me?
Yes.
All right, good.
Very well.
Yeah, so we are used to building these systems. So it's pretty fast to do. So it's the design of the board. Actually, I just found it again here. The design of the firmware, the design of the backend system. It's a 6 to 12 man months kind of effort for putting that together. That's kind of the and I'm sorry, I'm only talking about the low power wireless aspects. I'm not talking about the data analysis aspects. Luis maybe can fill us in on this.
Okay, and I've also a very stupid question. Why go to Chile as we have many fine vineyards in France and also frost events?
We have deployed in smart agriculture all around the world, and the phone rings all around the world, but not from France. So I think it says something about French, production.
Too bad. And by the way, do you have any plan on technology transfer, either to an existing company or startup, maybe?
We did look at the business case when so in 2019 we did create a startup selling these low power wireless systems. We did not select the smart agriculture as the main use case because the market wasn't ready or was a bit too small or too fragmented. Instead, we went to a different application, which is of monitoring boats in marinas. The market is just more understandable, more more addressable with a clearer product. I'm sure there's a lot could be transferred, but this particular application not what we have selected. What we have selected in 2019, but we're very used to these kind of transfer actions. So if there's an opportunity arises, then 100%, of course.
Okay, thank you. Now some questions from our colleagues. Why the system use a mesh topology instead of a star topology? Is the first question.
Yeah. So fair question, right? We are using a low power wireless mesh networking technology rather than star technology in smart agriculture, where people immediately think about LoRa. So the node to node distance with the technology that we're using is around 400 meters. And this is a very dense deployment, and there has not been any sort of problem of connectivity. So what the mesh gives us is extreme low power and extreme reliability, which we wouldn't get if we were to use something like LoRa. For bigger deployments, beyond a couple of hectares, it would make sense wouldn't it be great to have a combination of mesh on top of super long range radios? And so this is exactly what we did. So I have a PhD student that just presented his PhD, and we did a deployment of a 103 kilometer mesh network, which I believe is the longest mesh network ever built, by combining this mesh technology with long range radios and kind of getting the best of both worlds. So while in this particular case, it wasn't needed, for other cases where the deployment is hundreds of kilometers, it might make sense to do some best of both worlds approaches with long range and mesh. And this is kind of what we do in the lab. Thank you for the question.
So maybe one last question, if you can answer quickly.
Yes.
Is this resistant to basically rain and something like that? How the wireless protocol used manage channel perturbations like rain events?
It's the main feature of it. This is built for critical industrial applications, so it changes frequency all the time, scans the frequency and finds the frequencies that work. So it is exceptionally good at combating, in particular, external interference.
Thank you. So maybe some question for Andy. So I would start with the same question about, can you give us an idea of the size of this project, the cost or the number of person months involved?
So I can give you size in terms of persons, probably better than cost, because it's been over the past few years and it's been in multiple currencies. So I probably get the numbers all mixed up in my mind. Essentially, we've been using a team of about 4 people from Inria, Chile, as well as an advisor from France. Over on our side, there's been about 2 to almost 10 people involved in the project at any time, going back and forth with interacting on requirements, building the system, testing the system, as well as giving technical advice as well too. The Inria Chile team has a UX person, 2 full-time developers and a team lead. And they've been doing a great job and just plugging away at this thing year after year, putting out some good product.
Okay, thank you. Compared to the state of the art, what the collaboration with Inria Chile brought to your project?
So it's definitively we've gotten some good product out of it. I guess I cannot emphasize that enough. They're very easy to work with. We, as an observatory that's just coming online with a telescope that's never been built before, a lot of things change, and they change pretty rapidly. They have been able to turn the curves with us pretty quickly, be able to change things and technologies as we go around very easily. They're very easy to work with. We come up with new ideas and we can discuss them, and they can come back with better ones, which is even greater. So that's kind of it's been a very good partnership going forward. It's one of the reasons we continue to renew contracts year after year with them to get more work.
So we have questions about, do you guys have a plan on updating the UI during the lifetime of the telescope, which I guess would be quite long?
Yeah, we have that 10-year survey that we're going to do once we're finally done with construction. And of course, there's going to be updates and new instruments and everything else that goes along. We definitely don't want to keep too solid in technology for 10 years. You can only imagine how old and rusty that would get after a while. So we've kind of built into the system, like I said, a UI framework to allow us to build other things as we go forward. Inria's been very good about that. We hope to kind of start leveraging that pretty soon as well, too, to start building our own screens. So yeah, that's kind of built into the project as well.
And also we have a question about how did you test the design with the end users?
So there's multifaceted tests with this. Given that we are an NSF project, we have listed requirements that are specified and stored in our documentation profile. We have to go through and prove that we verified these and it actually works against these requirements. We have a list of observers and operators that have gone through and test out each requirement, and we write out some test cases for those, essentially. We're using the JIRA product to hold our test cases, to hold our requirements, put the test cases against the requirements, go through certain test cycles. We've been doing that a lot through our auxiliary telescope observing runs. So it's kind of working in our production system and able to verify and test during that process. And so it's been kind of a strict process that we go through, just simply because we have to prove that the money we're getting from the government is actually working towards what they want and to the scientific goals that are happening. But it pretty much shows that our project works, and it should work once we get into the actual observing of the main telescope as well, too.
So thank you, Andy. Now some question for Maurizio. The next project look very interesting. Are there any industry or partner in this project interested in a technology transfer or producing and maintaining a real product? Do you see that in some future?
Hi, Stefan, and hi, all the panel and all the assistants. Yes, there are some industrial partners working with us from the beginning of the project, and currently we have a larger partner also included. Not in order to sell directly what we are doing, but to construct new applications over it. So we're trying to build an ecosystem based on data in order to have new data mining applications. So yes, we have a few partners, and our intention is to have much more, actually.
Okay, so we have a question, a rather technical question about which is the similarity between by processing images and finding similarity by format, or does the algorithm recognize similarity in images of different formats?
Yeah,
common disease?
Yeah, it's a good question. It depends on what do you mean by format. If you said it's the file format, then there is mainly a single file format for medical images, which is DCM, DICOM. But probably it refers to the internal format, and that means if it's from computer tomography, or if it's from a simple radiography. And the thing is that currently we're working with similarity of the same organ, at least. Okay, so it depends on on the equipment, on the instrument, and the format. Um, so it's similarity between different diseases, basically. So it's that's what the latent space do, is to find similarity between segmentation, pathological segmentation, physiological segmentation, and classification of different diseases. And with that, altogether, we define what is the similarity.
So we also have a question of who is expected to be the end user of proximity. Would the patient be able to interpret the results of his scan based on the result of proximity?
Yeah, it's not the patient directly. The user are practitioners, medical doctors that can work with that. Well, we are targeting right now research, medical research, so differential diagnosis and that type of applications. But our objective is to go to the clinical side, in order to help, for instance, the medical meetings where you have a new case or weird case, you want to present that. And typically, medical doctors say, okay, I remember this old case that was similar. Here, if you search by content, you can find similar cases with the diagnosis, and not only diagnosis, the evolution of the patient in the possible future of this new case. So our idea is to help the medical doctor to have a better diagnosis and better treatment based on cases, not based on classification percentage, but in different cases that could help them to take good decisions.
Okay, thank you, Mauricio. We are reminded that it's time to close the session. So once again, thank you to Thomas, Andy, and Mauricio for sharing your experience with us today.
Thank you very much, Stefan.
Thank you so much.
Thank you all. Thank you, especially Stefan, for being the chair of this panel, of this session. And thank you all, the participants who attended to the second day of the Journées Scientifiques Inria Chile. And we want to salute Francois Cooney, Deputy CEO for Innovation of INRA, who joined us for the session today. We remind you that 2 more days of our REACH program are still to come. Remember, you must be registered for each day and for each part if you want to attend. If you haven't registered yet, you can go to the website Journées Scientifiques 2022.inria.cl and register for each of the part you want to join. Also, you can join us. You can follow the updates on our social networks. What is it? Is Inria Chile on LinkedIn and Twitter. It's the same, Inria Chile. Tomorrow we will have another day full of interesting activities. Finally, the topics and presentations also that you've seen today will be available on the web in a few days. For those who could not participate in this activity, we will be here waiting for you at 8:30 a.m. in Chile and 2:30 p.m. in France. Thank you for joining us today and have a very, very nice day.